Okay, let's attempt the IMO 3. It may or may not actually work. Um, what the heck is the statement though? Okay, so fix k at least 2. We would like an. Okay, what the heck? So first of all, does this even happen? Like, so for k equals 2, can I get a single example of a thing that does this? We want the identity, a sequence of positive integers satisfying an plus 2 times an plus 1 is equal to an times, sorry, an squared plus coefficient times an plus coefficient, right? So does this happen? And it's, I mean, okay. Like, the answer is technically yes, because the Fibonacci sequence works, right? Or, how does it go? It's like 1, 1, 2, 3, 5, 8. I forget how it goes. Sorry, it's not. It's like something about Fibonacci squared plus 1 being nice. Um. Fuck. What was it? Yeah, 5 times 13. Shit. That's actually off by index. That's like an plus 2 an equals an plus 1 all squared plus 1. Okay. Okay. Never mind. But, oh, actually, any linear recurrence will not quite work. Because it grows a little too fast. Right, like if I was trying to get some sort of linear recurrence, then that's not great. On the other hand, if all the AIs are equal, that's also not great. That grows to oh, this is so bad. Wait, actually, no, you can let them all be equal, right? We could just let. Okay, so there's a dumb example where ANs are constant and CI equals 0 for all I. That is a working constructions. Is the answer just gonna be if the answer is just constant sequences? That's kind of lame though. But yeah, linear recurrences won't work. Wait, also okay, like an equals n. Well, wait, actually, hang on. Wait, can't I just like let an be like n and it also works? Then like n plus 1. That is a polynomial in. Wait, okay, now I'm really confused. What the heck is the answer set gonna be? It's like what? Okay. What if I let an equals n plus 1? it's like, is n plus 2 times n plus 3 a polynomial in, yeah, I mean, well, actually just if an is a, is this true? Yeah, this is true. And like, I can do it with 100 too, right? Like, 101 plus 102, because I'm just shifting all the indices. Okay. Does any arithmetic progression work? Oh, actually 2 might work. Yeah, the answer could be APs. Because if I do like, if an is 2n, then like 2n for 2n, hang on. 2n plus 2, 2n plus 4 is equal to, so the question is this like, well, yeah, I mean, there you go. 2n squared plus 4, 8, 12, 6 times 2n plus 8. Okay, what if an is like 2n minus 1? Does that work? Should be fine, right? So yeah, AP is fine. I don't think you can do little 11. I think it's a little sensitive because there's like non-trivial number theoretic information. Actually, little o doesn't make sense because a single AI is enough to kill things, right? Like, if a of 100 is like slightly too big, then it might be prime, and then P of A99 will never work. I think every arithmetic progression just works based on this. And AP should be easy to check. And then it's just a question of like, how do you disprove the other crap? To which probably it's something somewhat asymptotic. So in particular, like, if you do the thing to get rid of, even for n equals 2, this might be worth doing. I'm not sure. But if you look at like an plus 1, an plus 2, an plus 3, like on the one hand, this is equal to P of an times an plus 3, and on the other hand, it's equal to like P of an plus 1 times an plus 2, which is the thing that can happen. For k equals 2, this is actually try an equals minus n. No, an is explicitly given to be positive. Can we look at the difference? So if I look at the sequence where A1 is 2 and everything else is 1, why does that not work? Uh it's like I need it's like weird cuz like you would think that if you have an entire polynomial, like maybe you can fudge just A1. Um because A1 is only read in the problem once. Um So it feels like like there should be like a little bit of flexibility, but apparently there isn't, which is weird. Like in what situations can I not just mutate the value of a1? Like if a n equals n, then if a n equals n for all n strictly greater than one, for example, if it's the identity for all n strictly greater than one, that identifies the polynomial. And then it's like n plus k, and then it's like p of a1 is equal to like 2 times 3, and it's supposed to uniquely... Okay. So, I guess what I'm getting at is, like, P injective seems pretty important. Because P is injective. Actually, injective is a misnomer. I should just say it's strictly increasing. In particular, injective. Which means that if you get a polynomial-like relationship for... Like, if the ANs are eventually given by a polynomial, then they're actually, like, coincide with that polynomial. So, this suggests, if we know strictly increasing, that suggests that I should be able to, try to go backwards in some way. Like... Is the problem that bad? I don't know. Okay, anyways, yeah, I don't know. So it's sort of like an plus k is... Yeah, I do like the ratio thing. It's like, so if an plus 3 divided by an plus 2 is like p of an plus 1 divided by p of an, and... Yeah, I want to do analysis, but I'm not sure exactly how. I think it's true that this implies that, like, something. What is this doing? Yeah, but I don't like. What does asymptotic mean? Like, you're assuming there is a limit. Like, I agree that if there is a limit, then it equals the thing you said. But I don't know that there is a limit or something. I think. Also, here's the problem with this. Like, I can pick any polynomial p and get a sequence AI that quote-unquote works. Except for the fact that the AI are not integers. Or, like, you could imagine... I don't know. Like, I don't know. Pick, like, p of x equals x squared, and then k equals 2. And then, like, then a1 is, you set a1 equals 1, and a2 is equal to whatever makes it, like, a2 equals, like, 2 maybe, or something? And then a3 is equal to, okay, so a3 is equal to half, or something crappy like that. And then a4 is equal, yeah, so you could, like, imagine making a sequence, and, like, the only issue with this sequence is that, you actually need the integer condition, because otherwise you can just do this and then recursively define an plus k equals, like, the previous crap divided by stuff. Because in general, a sub n plus k will be given by the product of... It's like p of an divided by, like, the other... So this recursion is determined by picking a1 up to ak and then letting... I mean, and it is a recursion, so it will give you, like, numbers. And the only question is, will those numbers be integers? And... yeah, I guess it's like, if the AI sequence grows at all, like, if a of n is at least... Wait a minute. Hang on. Shit. Sorry, that's a typo. Yeah, like... So I feel like I want to... If there's a repeated AI, like if p of AI equals p of aj, that feels pretty bad. Something's supposed to happen when that happens. Like the sequence being all constant, for example, I think. If there's no repeated AIs, then it is true that a of n is at least, like... For some large constant, like, sufficiently far off, an will always be at least... n? Is that true? If there's no repeats in the sequence, then the AIs get big enough that... fuck. It's annoying because sometimes they're in the numerator and sometimes they're in the denominator, and you really want... This is like an okay, in this example where I did 1 to 1/2, like what is the growth rate? It feels like it keeps this one will actually jump. It will oscillate, right? That's why I'm so annoyed. It's like A5 is equal to 1/32. Yeah, it's oscillating. Ah. So the integer condition is really important. Because otherwise, like, you can come up with arbitrarily dumb sequences that satisfy the condition. Did we actually prove P is strictly increasing? What do you mean did we prove P is a polynomial with non-negative coefficients and at least one positive coefficient. So it's strictly increasing over positive numbers anyways. I mean, is that for real? Okay. What's happening? I am trying IMO3 and not getting very much. But it's like... integers. I need to use the integer condition. I'm like not really doing it, and that's bad. Anyone feel like the difference of an plus 1 and a... Like, if I look at p of an plus 1 minus p of an, there are a lot of factors, right? Or at least like an plus 2 divides it. For large K, it's like a lot of factors, but I just can't deal with the oscillation. That's the problem. Like if I try to use pure size, I'm gonna die because of this green example. So I need to do something that like... Oscillation? Yeah. Like, if you drop the integer condition, you can get examples that are large and then small. For that matter, like, why is there... So, up until now, I found examples that were APs, like arithmetic progressions, and I wonder if there are examples where, like... It's like 2, 2, 4, 4, 6, 6 or something like that. Are there examples that look like that? No, they're like, well, no, actually. Once an plus 1 is strictly greater than an, do you get more increase? That's true. So if there's any indices for which, if you take an index for which this ratio is greater than 1... Well, no, the problem is that... Like, it transfers you to an plus k instead of an. So, if an is bigger than an minus 1, then... Yeah, okay, maybe I should use the strictly increasing distort or something. Like, we can... So, at least we have a statement like, if an is bigger than an minus 1, like, an is bigger than an minus 1 if and only if an plus k is bigger than an, or something like that. So, if, like... If a2 is bigger than a1, then a4 is bigger than a2. Is that useful? Well, the reason we know it's not number theory is because IMO1 was obviously in the number theory section. So this one is not. Also, the IMO4 was obviously in the algebra section. So we know this came from the algebra section. Yeah, I agree it's mostly analysis, it's just I need to use the integer condition somewhere. It's possible I only need the integer condition in so much as, like, every AI is at least 1 is a possible way to use the integer condition. That's probably not good enough, but... Yeah, yeah. So why is like an equals n squared not a solution? If I do like n squared plus n plus 1 times n plus 2, it's why is that not never a polynomial in n squared or something? Well, I mean, if a polynomial is okay, yeah, fine. Well, hmm. Hmm. Then an plus k is less than an. Oh shit, did I flip the... Oh, that's a good point. Okay. Yeah, it works better the other way. If an is... Okay. Then it's also smaller than an plus k. Yeah, okay, actually... So it's like I should look at the contour or something. Like, look at the shape of... You're right, this is actually like, I don't want to say transitive. But it's like if A1 is bigger than A2, then... Oh shit. Okay, so if an is bigger than an minus 1, so if it goes down, then later on then also, the small number also has a thing less than it. So then look at a point where... But these can go back up, right? Like, I just know an plus k is even smaller. But... oh, but it's smaller than the smaller number. Oh, fuck. Okay, fine. It's smaller than the smaller number, not the one before. Oh, okay, fine. Yeah, sorry. I keep flipping the order, so I got confused. But you are correct. So claim, so either AI is eventually constant. So, well, let me just say. This might like be the only place we use integers, honestly. Then it follows that an plus k is less than or equal to an is even smaller than an, so there is an index L between, like, such that there's another index L such that AL is less than or equal to AL minus 1 for L n plus 1 up to k plus 1. So it's like it's like an, okay, I need a picture. It's like, it eventually goes down, and then it's like AL, it should go down to an AL such that an plus k. So between an and an plus 1, there's a, take the lowest, and then there's something less than or equal to it. So if it strictly goes down, then it's equal, and hang on. Okay, yeah, let me do this slowly. Ah, this is so... indices. So we get infinite descent. Hence weakly increasing. And then to transfer to strictly increasing, repeat the same argument with an equals an minus 1 implies an plus k equals an, and so on, because we're weakly increasing. It's all good. Okay. Okay, that took way too long. Oh my god. It's smaller than the smaller number. It's not what I'm used to. It's, yeah, it's because we used the an. Okay, fine. So if you go down, then the next thing is even downer. Yeah. So in particular, the sequence grows at least as fast as So yeah, I feel like that bounds the growth of an plus k by a lot. Because now your sequence actually... Okay, this feels a lot better for asymptotic crap now. Okay, I should be careful and write, unless it's constant. Okay, so where were we? So here's the problem again. We know it's increasing, and we also have the recursion. So assume A1 is less than A2, less than so on. And we have this relation. And what I want to show is that an plus k is bounded by, like, something pretty reasonably small. Like, in particular, I really want it to be linear. Why did I say that n squared didn't work? N squared didn't work because, like, well, who knows? Yeah, PA of n is greater than an to the k, so... P of an is at least... Are you trying to lower bound it? I mean, we can do that. I was trying to upper bound it. Like, I want an plus k to grow, like, slower than things. Actually, for that matter, if I just take the, like, difference between these two, like, like something like this. Like, I don't know. It's just not gonna grow very fast. Like, I feel like I want to do some finite difference type argument now, where, well, finite difference, I'm only need to do it like a couple times. But like the idea is like an and a minus 1, like this difference shouldn't grow particularly fast. Because it's like... Right, because this bound here, yeah, I'm so glad I have this strictly decreasing now. Holy crap, that was like being so annoying for so long. Like, we can bound this by... But I don't want to bound them by... So I take the difference sequence, like the sequence of the differences between them, and then like P of... So I know the answers are, I suspect the answers are arithmetic progressions. If I take I don't know. I'm looking at like, yeah, suppose I have this interval from an to an plus k, and there's like a bunch of differences, okay? And like this is the product of, yeah, an is bigger than an minus 1. So this feels really, hmm. Can I look at consecutive differences? I'm gonna look at three things. I wanna show like the differences also don't behave badly or something. So let me actually write down three consecutive indices. It's like an plus 1, an plus k. Yeah, it's definitely O of n. Like this alone is already like I don't know. I feel like I'm running into like a same version of the issue before. Like earlier before, I was like, if it's monotonic, we're fine, but it's not. But it might not be. So I had to do this thing with like the integer condition to like pin it exactly. And I want to do something like kind of similar here, where like if the growth rate is actually if the it's like one more step where I'm using the differences instead of whatever they're called. Anyways, like it would be really nice if like a list like if a one difference was bigger than the next one, it transferred to like some other difference later being yeah. Yeah, I mean, what you can say here is that this is less than or equal to p of an times an plus 1, an plus 2, an plus k minus 1. So this is like less than or equal to an to the k plus like some constant an to the k minus 1. And then some crap in the bottom. So there's some constant depending only on p, not on the an, such that this is true. And so then when you do a division out, it's like an plus more constant. It's like c equals k minus 1 factorial or something like that. And then yeah, there's some constant c, which is fine. And then it's like some c prime. Yeah, so a sub n is sublinear, which is good. And I guess if we're working with integers, then you can actually do some combo where you say like, if you look at k consecutive differences or something like that. Well, actually, it's just sublinear, period. So eventually certain difference patterns have to repeat. I don't know if that's exactly how I want to go about this, but it's seems pretty good. I wonder actually if I could just bound the rest of it. Like, I don't know. Because I guess the reason like, if a sub n equals n squared-ish, that doesn't actually fail for size-ish reasons, right? No, wait. What am I talking about? I'm high. N squared is not sublinear. Actually, yeah, we can. Okay, I'm gonna try the dumb pigeonhole thing. All right. So because a sub n is sublinear, for any k, there's a pattern. There's a sequence d1, d2, dk of differences, such that for infinitely many indices n, we have a sub n equals a sub n. And this is because the di's are bounded. Okay. This feels so icky. This is such an Olympiad argument. Oh my god. So there's infinitely many indices n such that this works. And for all those indices n, we have p of a sub n is equal to a sub n plus d1, a sub n plus d2, a sub n plus dk. So p is actually exactly given by this polynomial. Oh my god, that's such an Olympiad argument. That's totally the kind of thing we do in high school, isn't it? Okay, so P is actually given exactly by this polynomial, and if that's true, then for every shit, sorry, I misspoke. It's like D1 plus D. Actually, you know what? We'll just, we don't need to nest the differences. We'll just do all of them by n. So there's a sequence of di such that this works. And if that's true, then starting from any index, I should be able to backwards propagate or something like that. I don't know. Or I can do number theory. That is also an option. Aren't you just done now? Explain why I'm done. Why am I done? It helps a lot though that we know it's, yeah, I agree that it seems like we should be almost there. Like I think after this, like now that we know P so exactly, we should kind of just be able to run it over. I almost want to do a bit of number theory now, because if we know that how this thing more or less factors, but it's not quite there. I agree that I agree that differences should all be the same. You can bound the GCD. Okay, let's write this out. So now we have an plus 1, an plus 2. For all n. The GCDs of any two terms on the right hand side divide some absolute constant. Not absolute constant, just some constant. D is product di. So if an is big enough, then because the things are all so close to each other, you cannot redistribute any prime factors, is the claim. Because if you tweak by a prime factor, you're multiplying by some scalar. When n is sufficiently large, no number of the form q times an plus di where all primes, see, this is number theory, all primes dividing either the numerator or denominator are q. will still lie in the interval an plus c prime. Right, so c is a constant, an is really big, and I can only... You have big numbers, and then like... the difference is at least... So that an is bigger than like c prime times... c prime plus like 1 over d. I think is the threshold. Sorry, not c prime plus 1 over d. C prime times d. Wait, shit, no, this doesn't... Am I high? I think I might be high. What am I doing? Sorry, I think I'm stupid. This doesn't work. This doesn't work. Sorry, no. Ignore everything I said. Yeah, this doesn't make any sense. I don't know what I'm writing. Yeah, we would like an plus I to be equal an plus d sub I. Well, if I show it, yeah. I would like them to be the same set, yes. I agree with that. Only one list of differences appears infinitely often. Oh. And everything else happens finding... Oh. Good point! Oh, yeah. Suppose a sequence of it appears for an element, then appears... And so, in particular, only one sequence of di appears infinitely often. Thank you, Warren. Yeah, okay. Yeah, so hence, for large enough n, we're fine. Yeah, this gives you periodic. Not only is it periodic, it's periodic with period 1. Yeah, it's not even di periodic. It's di is periodic with period 1. Or not periodic's not the right word. Actually, well, sorry. It's more confusing if I write it this way. Now that we're doing, sorry. We're gonna make it the actual differences, okay? D2 plus D1. Yeah, we're fine. We're good. This will do it. Plus DK. K minus... Hang on. Yeah, DK. There's a coefficient bash. Ha, sucks to suck. Yeah. Just, only one sequence appears for the object. Okay, we're done, right? Okay, this problem's not that empty. I think it's like, I don't know. I think it's not supposed to be a number theory problem, and you can tell. Like, I don't think it counts as anti if... Okay. Anyways. Okay, that happened. So, yeah, I think we conclude that IMO 3 is easier than IMO 5. Which is, we kind of knew already, but, Okay, first things first. We need to fix the LaTeX. Okay, wait, I don't remember the... I have a new toy, so I'm, like, learning how to use it. Begin. So M is for frame. Okay. Okay, R is frame. Got it. Fixed LaTeX. I mean, so I think the... I don't know. I don't know how long it would have taken me to notice. I think I would have gotten the increasing eventually, because I was just... I had the direction flipped in my head, so I thought it didn't work. I might if I was... I don't know how long it would have taken me to notice the only one difference appears infinitely often thing. I don't know. There's like a few steps, so it's like if you miss any of them, you're just kind of sad. Yeah, okay, let's write this up well. So the answer is whenever an... It is arithmetic progressions, right? Indeed, if an is equal to kn plus l, or I shouldn't use k. Fuck, I don't want to do the check. Can I just... Oh, actually, it's obvious. Never mind. If an is the n plus e for n, I was about to like manually expand. Then an plus 1. Let's take p of x equals Okay, so first thing, claim either. Oh shit. Either A1 less than A2 less than da-da-dun, or AI the sequence is constant. Okay, so note that polynomial P is strictly increasing over n. It follows that. Now, first we show. So assume for contradiction there's some index n such that an is bigger than an plus 1. Then an plus k is bigger than an. Oh, sorry. So there must be some. Let L be the smallest index argmin so be the index minimizing AL. Now AL is less than or equal to okay, so then okay, so now similarly if there's hence we have A1 less than or equal to A2. Da, da, da. Thank you, Winston AM, for the follow. It is constant. It is fully constant. Okay, cool, cool, cool. All right, and so now for the crux move, the big step was where he's like, okay, for each index n, we can consider the associated differences. Or no, actually, we have to bound it first. You have to bound it first. So claim an there exists a constant c such that depending only on k and p. actually. So, okay, let C prime be a constant such that P of x is less than x to the k plus C prime of x for all x in n. Well, let's just do it that way. Okay, that works, right? It's actually the actual constant is like k choose 2. It's like a to the k plus Did I get that right? No, actually the constant is on the bottom. It's like, wait. Oh, I suck at long division, sorry. No, it's on the top. Wait, hang on. Yeah, wait, there's no kitchen. It's literally. We can consider the associated differences d1. Consider the associated differences d1 equals an minus dn equals an plus k minus. Yeah, so we're being a little wasteful, which is normal. 2017 N4, is that the... Yeah. Yeah, that problem is... That problem is like a tutorial problem. Like, you do it so that you learn the concepts, but you wouldn't want it to be like the main show. Then d1 dk can only take up to c to the k value to... In particular, some tuple must appear only infinitely often. For that tuple, we obtain for infinitely many n. But because of that, we obtain... So we actually must have which we denote by delta n. There's also at most one that exactly one output to delta occurs infinitely often, because that output is determined completely by p. So consequently, follows that delta is eventually constant. For this to happen, an must eventually coincide with an arithmetic progression of some common difference. How do I know C exists? Because P of n is given... Oh, sorry, it should be C x to the k minus 1, not... For example, C equals C0 plus C1 plus CK minus 1 plus 1 will work. And P of x is equal to x plus dx plus 2d, x plus kd. Finally, this implies my downwards induction that an ta-da! All right. My jump is broken. Okay, I gotta deal with that later. Analysis, manip, size. I think this is reasonable. Good or nice? I'll classify as good. Find. Actually, it's not really manip. Okay, here's the URL. Okay, now for the part where I give a hardness rating. No, we're not putting it at 5. I'm wavering between like... I haven't decided for IMO 5, and I don't know if I can because I eventually died on it and had to read the solution. I think IMO 5 will be probably at least like 35, if not 40. And this feels easier to me than that. 25? 25 seems a little... I'm gonna go 30 for now. We might change it later. I'm gonna tentatively pencil in 30. I feel like there are kind of a few steps. Like, each individual step is not earth-shattering. Like, each individual step is like quite expected, but you do have to get them all. Like, you can't miss any of the inner. Or you can, but maybe you have to work a bit harder. Yeah, honestly, 50. I don't know if P5 is 50 because everyone on the IUS team, I think except one person got it. But it's high. I think 5 is quite tricky. Oh, yeah, P4 I don't think is 15. I think P4 I was... I convinced myself that I needed to do something that I didn't need to do. I think problem 4 you will... If you have enough... I think if you're very well trained, you will eventually solve problem 4. Like, it's just how much stuff do you try that doesn't work before you realize what's going on. But I don't know. Yeah. This is a good comment. Zymo 3. I don't feel like this is... I don't know. It feels a little too involved. It's like, I think it's too many steps to be 25. I agree it's... Yeah, I don't know. Like, I mean, if I didn't have the stream to, like, tell me when I was being dumb, I think it would have taken me a lot longer. So... I don't know. Honestly, I think if I go to this IMO, I get like 1, 2, 3, 4 or something. I'm assuming I'm not going to get 6 anytime soon. IMO 3 has less solves than 5. I don't know. I just feel like it's such a... I just feel like there's no trick. Like, it's... What you think is gonna happen, happens. And you just need to execute it. Like, maybe the most thing that was, like, weird was this, oh, you know, do this infinite pigeonhole on delta. But I think infinite pigeonhole is just, like, such an Olympiad argument. You know, I kept saying, it's like, oh, this is definitely the kind of thing you do in high school. It's like, just say, look, there's a function from an infinite set to a finite set. I think it helps if you know that problem 1 was NT. That does actually seem like a big advantage, is that the fact that problem 1 was on the paper is like, oh, it's definitely not... This came from the algebra section. So you're not going to be doing stuff with, like, random primes. Or whatever. I don't... I think this is, like, the first time that, like... I think seeing the... Like, knowing a bit about how the IMO test is put together actually mattered more than, like, comedic value. Yeah, I mean, it's not like a formal written policy, but it's just like, you would be very surprised if the jury votes to put 2 problems from the same category on the same day. Even though it happened in 2014, so rip me. God, I didn't get any number 3 on my IMO. It was really sad. General only slang? I don't... Do I want more slang in this world? Yeah, 2014 was, like, problem 6 was combo, and then problem 5 was N3 in quotes, and it was the Bank of Cape Town. So, number theory, because it had 1 over N in it. And yeah, but